In section 8.5, we look at polar coordinates. Polar coordinates is a new coordinate system for locating points in the plane. So we know that we have the x and y axis, which is called the Cartesian coordinate system or the rectangular coordinate system. And we locate a point in this manner by simply lining up the x-coordinate on the x-axis and the y-coordinate on the y-axis, and that gives us the ordered pair xy. And this is the way that we locate points in the plane currently. But there is another way to locate points in the plane. Instead of giving the x-coordinate and the y-coordinate, if you draw the corresponding right triangle, you'll notice that there is a number r represented here, which is essentially the distance that this point is from the origin. And also there is an angle theta rotated from the positive x-axis to this line. So we can use this value of r and this value of theta to give the coordinates for a point. And then when we do so, we call this r theta. And the definition for polar coordinates is that this ordered pair r theta names a point that is r units from the origin along the number line, which we call the polar axis, that has been rotated through an angle theta from the positive x-axis. The coordinates r and theta are said to be the polar coordinates of the point that they name. And in polar coordinates, the origin is sometimes referred to as the pole. So just for clarity, what you see here is basically we have the rectangular coordinate system, and we are talking about points in polar coordinates based on this rectangular coordinate system. But technically, you don't have to have a rectangular coordinate system at all. The line here, the positive x-axis, this line here, is often called the polar axis. And the point at the origin is not sometimes called the pole, it is called the pole. Now in this class, we will loosely refer to this point. Sometimes we will call it the pole and sometimes we will call it the origin just because of familiarity. But technically, the polar coordinate system just consists of this ray. So you have the pole and you have the polar axis, and from there you rotate through an angle theta and you go out a distance of r to get to the point. So this gives us another way to describe points in the plane. Now each of these systems has advantages and disadvantages. The advantage of the rectangular coordinate system, our normal coordinate system, is that when you describe a point by giving its x and y coordinates, those points are unique. But when you describe the coordinates of a point by using polar coordinates, those points are not unique. Now, why is that? Why are the coordinates xy unique while the coordinates r theta are not unique? Well, just think about the nature of the coordinates. The x-coordinate of a point refers to the number on the x-axis, and there is only one such number. And the y-coordinate of the point refers to the y-coordinate of the point on the y-axis, and there's only one such number there. So the x and y coordinates are unique. However, theta is not unique, right? So to get to this angle, I can rotate through this angle of theta, or I could also rotate a whole revolution and then stop here, right? Those are the same angle, or at least they terminate in the same place. So when I have theta, really, theta is equivalent to theta plus 360 degrees times k, right? Because if I take the angle theta and I add to it any multiple of 360, I end up in the same spot. So the thetas are not unique. And as we'll see in some coming examples, the r value is also not unique, but I'll describe that in a little bit. Let's take a look at some basic examples. So first, let's just take a look at an example of graphing points in the polar coordinate system. Now you'll notice that the graph that I have here is a little bit different than the graphs that you're used to seeing. So we do sort of have an x-axis and a y-axis, but you'll notice that there are no negative values on here. And that's because these numbers describe r. So they describe the distance from the origin. So let's go ahead and graph a couple of points to see what we mean here. So for the first point, we have the point 345 degrees. So when graphing a point in polar coordinates, normally what we do is we go to the angle first. So I want you to notice that 45 degrees is this angle right here. So we know that the point is going to be somewhere on this line, and then the 3 simply tells us that we need to go 3 units from the pole, or 3 units from the origin. So if we go 3 units in the direction of 45 degrees, you can see that we have these marked off here. So this is 1 unit, 2 units, 3 units would be here, but in the direction of 45 degrees. So the point 345 degrees would be located here. We'll call this point A. For the next point, we have 2, 120. So again, to locate this point, first thing we're going to do is locate 120 degrees. And this is really easy to do in this coordinate system because I have the basic angles here displayed. So 120 degrees is here, and the 2 means we're going to go 2 units in that direction. So that point would be right here, and we'll call this point B. So this point is point A, this point is point B. Now the next 2 points are a little bit more interesting. You'll notice that in the next point we have an angle of 60 degrees, but the R value is -4. So we need to talk about how to deal with that. So the first thing we do is we go to the angle 60 degrees, and we'll go ahead and represent that. So 60 degrees is this angle right here. Now, if this number were +4, we would simply go 4 units in this direction, which would put us at this point. But because it's -4, what we do in this case is we go in the opposite direction. So if we continue the angle 60 degrees in the opposite direction, we get this angle. And if we go 4 units in that direction, we end up with this point right here. And we'll call this point C. And finally, let's talk about the point -5, 150 degrees. So once again, the first thing we do is we locate 150 degrees, which is this angle here. And again, if it were +5, we would simply go 5 units in the direction of 150 degrees, which would be this point. But because it's -5, we have to go in the exact opposite direction, which means we end up over here, 5 units away from the pole. So that last point occurs right here, and we'll call this point D. So this is how we graph points in polar coordinates, and in particular, this is how we deal with the R value when R is negative. Now, up until this point in the course, R has never been negative. So if you think about the things that R has represented the hypotenuse of a triangle. R has also represented the modulus of a complex number. And in both of those cases, R is always a positive number. So for the first time, when using polar coordinates, we allow for R to be negative. In the next example, we're going to talk about why polar coordinates are not unique. So in this example, it says, give 3 ordered pairs that name the same point as the point 360 degrees. So let's go ahead and graph the point 360 degrees. So we go to the 60 degree angle, and 3 units out from there, we get that point. Now, what we know is that this angle right here is 60 degrees, and we know that R is equal to 3. So if I want to give some alternative representations of this point in polar coordinates, the easiest way to do that is to change the value of theta. So right now the value of theta is 60 degrees. But I could take 60 degrees and add 360 degrees, which would give us 420 degrees. That would be another suitable value for theta. And if I do that, the point would simply be 420 degrees. So to graph that point, you would rotate all the way around to 360, and then 60 more makes 420, so you would still be on the same angle, and then you would simply go 3 units in that direction. But another possibility for theta is I could take 60 and subtract 360 degrees, which would give us negative 300 degrees. Negative 300 is the same angle because basically we're just going around in the negative direction. But negative 300 degrees still ends up in the same spot. And so I could choose to use theta equals negative 300 degrees. So both of these would be alternative representations of the same point. And that's why we say for a particular point, the polar coordinates are not unique because any one of these three gives you the same point. Now, we could keep doing this. So I could keep on adding 360 or subtracting 360 to get additional angles. But the other thing that I could do, as you saw in some previous examples, is I could use the opposite angle. So we know that 60 degrees is here, but if you go in the opposite direction, this angle would be 240 degrees, right? You can see that here. Now, if I use an angle of 240 degrees, my R value would have to be negative because a negative R value would bring it back across. So another representation of this point would be to take R equals negative 3 and to take the angle 240 degrees. Now, the quick and easy way to get that is to simply take your original angle, which was 60 degrees, and instead of adding a full revolution, you simply add a half revolution, right? So you add 180 degrees. And then when you do that, your R value now has to be less than 0, has to be negative. So here I've given 3 additional polar representations for that same point. And this is why they are not unique. Now let's talk more generally about polar coordinates and rectangular coordinates. So here I have the same picture that was on the first page. We have a point which can be written in either rectangular coordinates or polar coordinates. And you can see the X and the Y here are the legs of this right triangle, and R is the hypotenuse, and theta is the reference angle here. So if we want to convert from polar coordinates to rectangular coordinates, or if we want to convert from rectangular coordinates to polar coordinates, we need to have some formulas that relate the values X, Y, R, and theta. Well, the formulas are given down below here. X equals R cosine theta, Y equals R sine theta. R equals plus or minus the square root of X squared plus Y squared. And tangent of theta equals Y divided by X. Now, all of these formulas should be really kind of obvious, but let's go through them just to make sure you understand where they come from. So using basic right triangle trigonometry, we know that cosine of theta is the adjacent side divided by the hypotenuse. So that would be X divided by R. And if you solve for X there by multiplying both sides by R, you get X equals R cosine of theta. Likewise, sine of theta is Y divided by R. And if you solve for Y, you get Y equals R sine of theta. So that's where these two formulas come from. Now, what about the other formulas? Well, again, this is basic trigonometry. We know that tangent of theta is opposite over adjacent, which is y over x. So that is where this formula comes from. And finally, we know that x squared plus y squared is equal to r squared. And if you solve for r by taking the square root of both sides, we get r is equal to plus or minus the square root of x squared plus y squared. Now, normally, for most of the other things that we've done in this course, we would just take away the negative, and we would only have the positive here. But for polar coordinates, we know that r can be negative, right? We talked about that. So for the first time, we have to have plus or minus here. So let's do some examples of converting polar coordinates into rectangular coordinates. Now, I have a graph here, but as it turns out, you don't actually have to graph these to do this. But let's go ahead and do the first one using graphing, and then I'll show you how to do it without. So the point here is 430 degrees. Let's graph that point. So we go to 30 degrees, which is right here, and we go out a distance of 4 units. 4 units is right there, and I'll put a point there. And then you can make a right triangle. We know this angle is 30 degrees. We know the hypotenuse is 4 because of the given information. And we know that this triangle is a 30, 60, 90 triangle. So this leg over here is opposite 30 degrees. So it has to be the short leg. And the short leg is always half of the hypotenuse. So we know this is 2. And then the longer leg of a right triangle is radical 3 multiplied by the short leg. And so that's going to be 2 times radical 3. And so you can see your x-coordinate is 2 radical 3, and your y-coordinate is 2. So the point 430 degrees, when you convert it into rectangular coordinates, is 2 radical 3, 2, right? So here we have the r theta, and here we have the x, y. So this is one way to do the conversion. Now, this really only works well if your triangle is special. So if your angles are not special values, you might struggle a little bit more with finding your x and y value. But we have formulas for this, so we don't have to actually do it this way. So the quicker, easier way to do this is to just remember that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And for this problem, we know that r is 4 and theta is 30 degrees. So if I just plug those in, x is going to be 4 times the cosine of 30 degrees, which is 4 times the square root of 3 over 2. And when you cancel the 2 here, you get 2 radical 3. And y is r times the sine of theta, so that's 4 times the sine of 30 degrees, which is 4 times 1/2, and 4 times 1/2 is 2. So x is 2 radical 3, and y is 2. And if we write that in an ordered pair, we get this. So the graph here is completely optional. You really don't need it. For the second one, here we have r equals negative radical 2, theta equals 135 degrees. Again, you could graph it, and if you feel the need to graph, go ahead and graph it. I think it's good practice to graph these. But we can change this to polar coordinates, change it to rectangular coordinates by simply using the formulas. So once again, x is going to be r times cosine of theta. R is negative radical 2. Theta is 135. So it's negative radical 2 times the cosine of 135. This is negative radical 2 times the cosine of 135 is negative radical 2 over 2. And so what we get here is positive 2 divided by 2, which is 1, right? So negative times negative is positive. Radical 2 times radical 2 is 2, and then divided by 2. And for the y-coordinate, y is negative radical 2 times the sine of 135 degrees. And this is negative radical 2 times positive radical 2 over 2, which is negative 1 divided by 1, which is negative 1. And so the rectangular coordinates here would be 1, negative 1. And I'm going to draw a graph just to make sure you understand where that came from. So if we graph the point negative radical 2, 135 degrees, first you would go to 135 degrees, which is over here. And then because it's negative radical 2, we'd have to go in the opposite direction. The opposite direction is this way. And radical 2 is approximately 1.4. So if you move 1.4 units in that direction, well, this is 1 unit. This is 1.5 units. So 1.4 units in that direction is approximately right there. Now, it's a little bit harder to see this, but if you draw a triangle there, a right triangle, this is radical 2. You know that this angle is 45 degrees. So we have a 45, 45, 90 triangle there. So the x value here is 1, and the y value is negative 1. Right? And that's what we got. We got 1, negative 1. But again, it's just much more efficient to simply use the formulas. And for the last one, we have the point 3, 270. So r is 3, theta is 270 degrees. And so to convert this into rectangular coordinates, x is going to be 3 cosine of 270 degrees, which is 3 times 0, which is 0. And the y-coordinate is 3 times the sine of 270 degrees, which is 3 times negative 1, which is negative 3. And so in rectangular coordinates here, the point would be 0, negative 3. Now let's do some examples of the opposite. We want to convert to polar coordinates. So here we are given rectangular coordinates, and we want to convert to polar coordinates. So again, I think graphing is a good tool here. I think graphing helps to solidify your understanding. So we could graph the point 3, 3. To graph the point 3, 3, you would have to go to x equals 3, which is right there, and y equals 3, which is right there, and line up those points. Now, those points don't line up naturally. You have to kind of line them up yourself. They would be right about there, okay? And then to find the polar coordinates for that, you could make a right triangle like this. Now, it's pretty clear that we know this angle here is 45 degrees, right? Because this is 3 and this is 3. And then you could solve for r. To solve for r, you could use the Pythagorean theorem, or you could just use the formula for r. Right? So let's remember that r is plus or minus the square root of x squared plus y squared. And so for this particular example, r is going to be plus or minus the square root of 3 squared plus 3 squared. This is plus or minus the square root of 9 plus 9, which is 18. And that's plus or minus 3 times the square root of 2. Now, if I choose my angle to be positive 45 degrees, then I would choose my r value to be positive 3 radical 2, right? But as you know, I could pick the angle to be over here, right, opposite from 45 degrees. And if I choose this angle, then my r value would have to be negative. So what am I saying here? Well, the hypotenuse here is 3 radical 2. So one possible representation would be 3 radical 2, 45 degrees. And then, of course, I could give you any angle coterminal with 45, but, I would recommend just keeping it simple. But if I choose r to be negative, then we would have negative 3 radical 2, and then the angle would have to be in this direction here. And that angle is 225 degrees, right? So there's a couple of different possibilities. Now, normally when you're asked to convert to polar coordinates, they won't ask you for more than one answer. Normally, they will tell you to give an angle between 0 and 360, and normally they will ask you to give a positive r value. So this is sort of the more basic and perhaps the better solution, but I just want to mention that, once again, when you're converting to polar coordinates, there is not one unique answer. Okay, so this is part A. For part B, we have the point negative 2, 0. So what I could do here is go ahead and graph the point negative 2, 0 in rectangular coordinates. So that's x equals negative 2, y equals 0. That's right here. And this one's really simple because it's on the polar axis, right, or the x-axis. And you can see very clearly that the distance there is 2 units, so r equals 2. And it's also very clear that theta is equal to 180. So if I give a single coordinate for this, I would say r equals 2 and theta equals 180. And for the third one, part C, we have the point -1 radical 3. So again, we could graph this, go to the point -1 on the x-axis, which is right about there, and radical 3 on the y-axis. Radical 3 is about 1.7, so this is 1.7 is right about there. Line those up, and you can see that we're talking about this point right here. And then, you got to find your r, and you got to find your theta. Now, you can use basic right triangle trigonometry to figure this out. So we know that this is -1. We know that this is radical 3. And from that, we could find r, right? We know r is going to be 2 because this is basically a 30, 60, 90 triangle. But if you didn't recognize that, you could figure those things out. So once again, you could find r by saying plus or minus the square root of x squared plus y squared. And this would be plus or minus the square root of 4, which is plus or minus 2. So that means you have the choice of choosing positive 2 or negative 2. We are going to choose positive 2. And then to find the angle, we know that tangent of theta is equal to y over x. So that means that tangent of theta is equal to the y value, which is radical 3, over the x value, which is -1. And that means that tangent of theta is negative radical 3. But now to find the actual value of theta, we don't use this. We have to talk about the reference angle. So the reference angle theta hat would have a tangent that is equal to positive radical 3, right? Because when you use a reference angle, you never get a negative value. And the reference angle would be the inverse tangent of radical 3, and this is 60 degrees. Okay, so that's a way that you can actually find that this angle is 60 degrees if you don't recognize that you have a 30, 60, 90 triangle. But the angle theta itself, let's remember, is this angle. And that angle, of course, is 120 degrees. So in short, this point converted to polar coordinates would be r equals 2, theta equals 120. Next concept is equations in polar coordinates. So equations in polar coordinates have variables r and theta instead of the variables x and y. The conversions we use to change ordered pairs from polar coordinates to rectangular coordinates and from rectangular coordinates to polar coordinates are the same ones we use to convert back and forth between equations involving polar coordinates. All right, so what is an equation in polar coordinates? Well, what's an equation in rectangular coordinates? So in rectangular coordinates, we're used to seeing equations like y equals x squared, right? And we know that y equals x squared has a particular set of points that correspond to it. In polar coordinates, we're going to see equations that involved r and theta. So you might see something like r is equal to the cosine of 3 theta, something like this. And the graphs for these things get really, really interesting. In fact, let me bring in the graph to show you what this graph would look like, just for fun. So what you can see here is that the graph of r equals cosine of 3 theta makes this kind of flower-shaped graph. So if you were to trace out this graph, you would trace it like this. And you could find these points by plugging in some theta values and getting some r values and getting all those points and then connecting them. But it's kind of difficult to get these graphs if you just plug in points. So one of the things that we like to do with polar equations like this is we like to convert them into rectangular equations. And please understand that in this course, this is just a small introduction to this concept. You're going to talk about this more in pre-calculus and calculus. Let's take a look at an example. Suppose you are given the equation r squared equals 9 sine of 2 theta, and you want to convert this into rectangular coordinates. you need to remember your conversion factors. So your conversion factors are, we know that r squared is equal to x squared plus y squared. We know that x is equal to r times the sine of cosine of theta, and y is equal to r times the sine of theta. And finally, tangent of theta is equal to y divided by x. Now, we don't use this last one very often, but the first three we use extensively. So if I'm going to change this into rectangular coordinates, basically what I'm doing is I'm changing all of my r's and thetas into x's and y's. And you'll notice that we have a sine of 2 theta, but over here we don't see anything with sine of 2 theta. So the first thing I would really want to do here is convert sine of theta by using a double angle identity. And if I do that, this becomes r squared equals 9 times sine of 2 theta, remember, is 2 sine of theta cosine of theta. And this gives us r squared is equal to 18 times the sine of theta times the cosine of theta. And from here, we can apply some of our conversion factors. So first of all, we know that x equals r cosine of theta. That's the same thing as saying cosine of theta is equal to x over r. And y equals r sine of theta is the same thing as saying sine of theta equals y over r. And from here, I can directly substitute those quantities in for sine and cosine. So what I have right now is r squared equals 18 times y over r times x over r. And you can see right now we're kind of in no man's land, right? We're in the process of converting our r's and thetas to x's and y's. So you can see at this point we have some x's and y's, but we still have some r's that we need to get rid of. So let's go ahead and simplify this. This is r squared equals 18xy divided by r squared. And if I multiply both sides by r squared, we get r to the 4th power is equal to 18xy. So now we got to say, well, what is r to the 4th power? Well, we know r squared is x squared plus y squared. So if I square both sides of this, I get r to the 4th power is x squared plus y squared, quantity squared. And this can be substituted into here. And when I do that, I get x squared plus y squared is equal to 18xy. And this is the equation in rectangular coordinates. So this equation that we started with up here and this equation down here, those are the same equation, just in 2 different coordinate systems. So this is what we mean when we say change a polar equation into a rectangular equation. One final example, we'll do the opposite now. Let's take a rectangular equation and change it into polar coordinates. This one's a little bit easier. So we start with the equation x plus y is equal to 4. And from the previous page, we know that x is equal to r cosine of theta and y is equal to r sine of theta. And I can put these in for x and y. So we get r times the cosine of theta plus r times the sine of theta is equal to 4. So at this point, I've completely eliminated x and y, and I have r and theta. But normally when we have a polar equation, we want to write r as a function of theta if possible. So that means we want to try to solve for r if we can. And we certainly can solve for r here. One thing I can do is I can factor out the r, which gives us cosine of theta plus sine of theta equals 4. And then finally, I can divide both sides by cosine of theta plus sine of theta. And you can see that the equation in polar coordinates is r equals 4 divided by cosine of theta plus sine of theta. So we have taken this equation in rectangular coordinates and we have converted it into an equation in polar coordinates. And once again, these equations give you the same set of points, just in 2 different coordinate systems.